Okay, while I'm having my late to breakfast and recharging up this webpage here, I'm going to talk about what we're going to talk about. Hopefully. I know I've been through this a few times and we're going to go over it again. Possibly in a little bit more detail, but a little bit quicker. Gotta get some food into me. So, there's a couple things I want to get into. Why isn't this web page cycling up here? Oh my god, I can't even find anything to do it with. I'll just read through some of this while I'm munching out here. It says geranium breaks down at 180 degrees Fahrenheit. Wouldn't transistors just melt at that temperature anyway? Transistors are used for amplifying and switching. That's my bird in the background. I'm looking at what's called an op amp right now. The first ones, I guess they came out in a can. This was invented in 1967. I started college back in the late 70s, about 10 years after this thing was invented. Not a long time. This is the schematic symbol for an op amp. It has a plus and minus input and an output. It's generally an amplifier. The AOL isn't called an open loop gain. So if you leave it open, it has a gain of 100,000. That makes it unstable. You can use it to act like a comparator, but there are other comparator circuits that use op amps. They're built different, I think. We should look at that too, as a matter of fact. Cut it out! Cut it! Goddamn fucking bird. These symbols here are transistors and resistors, and they are set up differently. I don't know if that V plus and V minus is V in. It might be. See here, it's taking. Yeah, that doesn't look right. There's an LM339. Oh shit, you know what? My microphone's not over here. There we go, it should make a little difference. So you can see there's diodes, there's transistors kind of linked together on the right here. And then you've got an output transistor and such. And if we look at the op amp inner workings, see, here's the problem with this is why well, it's so hard to explain this crap. So we've got your inverting and non-inverting input here. A bunch of little amplifier stuff going on. There's a differential amp, a class A amp stage. This is all the stuff that's built into this op amp. And why we can't use this in our circuitry is because of interference and interaction between the outside world, noise really. Actually, I don't want to look at that differential amp. So you can see there's a lot of components in there. You can use them for different applications. Like last time we were talking about negative impedance, negative resistors, and all that sort of thing. As a basic comparator circuit, you can see that that these circuits break down to basic transistor and resistor circuits and such. So that's an important thing to know, because we might want to build something that is called discrete, where it just uses transistors and not these op amps. That's kind of a basic circuit, a basic amplifier circuit. RF is your feedback. That's what we did. We tested the op amps to make sure they were good. And that's the circuit we used. V out is approximately equal to minus V in times RF over Rn. And it's minus because if it's an AC signal, the output is 180 degrees out of phase. And if you want to bring it back into phase, you put another op amp at the output and use a unity gain amp, and then just that reverses the phase. So getting back to transistors. I'm not going to go into too much detail. There's NPNs where the emitter points out, meaning no point in. And there's a PNP where the emitter points in please. That's the little nomenclature to remember that. So basically, you provide what's called a bias, and let's see, we'll look up transistor circuit. You know, I just realized we'll have to stop this music. I don't know if it's going to be ending up being copyrighted music or not, and I have to start all over my conversation. And I've got to start all over again because I left the mic off. Well, anyway, I was saying earlier that the op amp has resistors, transistors, capacitors in it, and such the same as the comparator, but they're in different configurations. And so those are not called discrete circuits. A discrete circuit uses discrete components, which is just transistors, resistors, op amps, that sort of thing. So this comparator is like an op amp, but it has different inner workings, but it's still not discrete. But we're going to try to use it to separate noise, and how that's done is two signals are put in. One signal is the reference, which is just the noise, and then the other signal is the signal plus the same noise that you're putting in down here. And so what you're doing is you're comparing the two, and supposedly all that's left on the output is just the signal. Supposedly. I haven't actually done this electronically, and at some point this is where we're going with all of this. Now usually a comparator determines a certain voltage, and it shuts on and off, that type of thing. And it's possible that if we put a large enough signal on the positive input over the noise, it's only going to let that signal in, regardless of what the noise is doing. There's some comparator circuits in there. See, it's comparing a reference information. Well, that's a comparator. Let's go to transistor circuits. Here's a nice transistor circuit right here. You have the base is the center lead, the collector is the lead where there's no arrow, and the arrow is what's called the emitter. Now, generally there's a DC voltage across the emitter. The emitter is actually a diode. It's just like a regular diode. And so what happens is a voltage comes into the base, it's a small signal level, and it turns the transistor on and off in relation to the voltage that's coming from where it says VCC 9 volts. It comes down through the 4.7K resistor, through the transistor, and down through this temperature compensating network. That's most likely what this is. And so, because there's 9 volts here, the small signal turns this transistor on in relation to 9 volts. So it's amplifying, it's sending the same information in the transistor, but it's amplifying it in relation to the 9 volt output. R1 and R2 are connected together, and they provide what's called the bias for the transistor. And generally they're the same. You can use R1 a little bit bigger, like a 10K and a 5K or something like that, but usually they're the same voltage. And a capacitor is put in here at the input to block DC from going into the input signal. Let's just take a look at this web page real quick here, and we'll see what it has to offer. You can do that all day long, I don't care. This filter setting, high pass filter of 300 Hertz. There's no filter in there. Okay, now in this circuit he's only using plus 9 volts in ground. Now he calculates the RC, which is the current resistor. That's this RC up here. He calculated that by taking VCC minus VC, which in this case I guess is 4.5 volts, and the current is 1 milliamp. How he decided that, I don't know. Use the data sheet of the transistor to calculate it. We will use a value of 1 amp for current. The max IC is 600 milliamps. That's the gain. HFE is the gain of the transistor. Collector emitter volt is 1 volt. DC current gain. Some other stuff in there, but I'm not going to get into all that. RC is an emitter resistor, so there has to be an emitter resistor. We have already set RC to 4.7K, and RE is already built into the transistor. RE is called the trans resistance, which is calculated as such, 26 ohms. So the gain is 180. However, the trans resistance is unstable. This person recommends, recommends a value of VE equal to 1 volt to stabilize the transistance instability. Which is interesting. So let's take a look at God. So you set up this using 4 resistors. Below is an example of H biasing. By choosing appropriate values, we can achieve good bias stability. In the end, it is needed quite a fair amount of knowledge on electronics and feedback stabilization theory to fully appreciate this technique. Here they're using 1K. So in other words, a DC voltage of 1 volt from emitter to ground we can add a capacitor in parallel with the 1K resistor that will effectively make the 1K resistor disappear from our spike signal. We want to add the capacitor anyway, as we need to make a high-pass filter. So they're making, well, it's also for temperature stabilization, but he's putting a bigger filter in there, a bigger capacitor. We want to pass our 300 hertz. That's actually a cutoff frequency. And I don't see how that's a high pass filter because the capacitor's in the wrong configuration. All it remains is any DC offset in the input signal to make it stable. Let's just set it to 1 microfarad. This also is called a BJT, which is a bipolar junction transistor. We also have FETs, which are called field effect transistors. They're more sensitive and act differently, but they have the same setup in the amplifier section. See, those resistances are different. We could probably run multisim and build this. Cockroach leg. What the hell? Brush the cockroach leg with a toothpick. Huh. A two-stage amplifier. Oh, it's using the same components. Why the hell's using a cockroach leg? That's disgusting. Strange. That's basic transistor design anyway. I mean transistor circuit design. Let's try something here. Let's bring up the web page again. I'm going to some of this stuff you can't see, can you? Let's see if we can build that circuit real quick. I mean, it does look interesting, I guess. Resistors. Resistor there, resistor there, resistor here, resistor there, capacitor there. BJT, NPN, 4T, virtual, PNP, virtual, battery, 0.7 and 1. Alright, now let's see what connect this. Now we want to add a generator. And if we look at the generator, it has an output on the bottom. It's supposed to go to ground. We've got our complete circuit. That's just that thing there. We're gonna want a couple of meters, I think. So the first voltage we want to measure is the bias voltage. And the second voltage we want to measure is the voltage here. And then we're going to have our illustrious Agilent scope. If I can just put it right there. There's channel A. And ground is that third block. Ground. A is going to be our input signal. Now, if we look at the function generator, there's a sink here, a sink output. If we look at the scope, there is a trigger. So you want to trigger on the input. So we've got our two voltages, our scope monitoring the input, and the output signal is going to be channel B, which is right there. Now we'll bring up our meters and turn them babies on. We're measuring DC. Turn our generator on. And of course the scope takes up the whole kit and caboodle. You won't be able to see everything on this, will you? I can't even see everything. that after I turn the switch on here. Alright, so we've got our bias voltage. That's showing 0 volts. It says it's open right now. He said that was a high pass filter, so anything above 300 Hertz should go through. Let's turn on the scope here somehow. There's a signal there, but it's awful low. Oh, it's 100 millivolts peak to peak. We have to look at channel 2. So this circuit's got some issues. Why is that clipping up there? Let me do an AC couple. That's 2 volts peak to peak. Or rather, that's a 2 volt. That's reading about almost 4 volts peak to peak on the output. Oh, maybe we've got to amplify that somewhat. Now there's a 1 volt peak to peak signal, you can see that perfectly. On the output we've got quite a mess, if you ask me. It has to do with that capacitor. I don't know what kind of circuit he was building by putting that big capacitor in there. Let's change the frequency and see what happens here. That's the low pass, lower frequencies. Let's go above 1 kilohertz here. So yeah, I think there's a problem here because there's supposed to be some voltage there. I don't know what's going on here. What we're gonna do is let's just move this out of the way. I want to measure. We've got 1.18 volts from base to ground. I want to measure the voltage from the base to the emitter. From base to emitter, and I want to change this capacitor to a much smaller value. Our scope set to, our generator is set to 3 kilohertz. Now we can change that to 1. Amplitude, let's set it back to 500 millivolts. Peak to peak. Bring the scope back up. Now we should see either 0.3 volts or 0.7 volts on this. And my web page is not refreshing or something. Now as far as noise goes, there's not going to be hardly any noise in this because this is what's called an ideal circuit. It's 700 millivolts, that's 0.7 volts. So it's acting like a silicon diode, I think. Okay, that looks much better. See, that capacitor, I think it was doing something not good. So the input's 500 millivolts peak to peak. We're looking at now it's reading 1, 2, 3, 4. Yeah, 500 millivolts peak to peak, and the output is that's the 1 volt scale. So the input is that large curve, and let's see if we can just keep it there for a longer period of time here. Alright, so you can see this, the smaller one, the smaller curve is reading 1 volt per division. So the output is actually 2 volts peak to peak. And the input is reading 100 millivolts per division, and it's reading 500 millivolts. So you've got 500 millivolts peak to peak going in and 2 volts going out. So you can see there's a gain there, and it's a perfect sine wave because of the frequency limitations of that capacitor. There's a different capacitor. Now there's DC coupling on the input, but there's no DC. Channel 2 is AC coupled. So, and the reason for that is because there's probably a DC on the output. It's up here somewhere. So that's reading 2 volts per division, so that's 2, 4, 6. It's sitting right about 5 volts, probably 4.7 volts DC on the output. Because when we look at the circuit, it's measuring right across, right at the output here on channel B. There's no capacitor, so that's why there's a DC. Normally you put a capacitor on the output as well to block DC from getting into your circuit. I didn't put one in there. That's all that is. It's nothing serious. That's something that's easily changed. So we'll go back and change this to AC. I can bring this up a little. Okay. Now let's change the frequency here. Oops. It looks like the phase is changing a little. See, that's 180 degrees because the peaks are actually, yeah, it's 180. But I think when I went up to 300 kilohertz, the phase is moving a little bit. I think the gain changed too. Is it going up? See, that's 2 volts peak to peak at 10 kilohertz. If I go at 300 kilohertz, it's actually going up. The gain is going up. So it's a high pass filter, but it's a lot cleaner, you know. The scope's taking a long time to read that. There's a lot of amplification there, and it's distorted at the higher frequencies. Now that's distortion, is not noise, it's due to clipping. It's amplifying too much or something. There's some distortion there on the top. You can see the top of that output curve is just it's got distortion in it. See how it's not perfectly symmetrical like the bottom? Now, this would be a good circuit to build, because it's slowly, by increasing the frequency up to 500 kilohertz, it's starting to show distortion. Let's bring it down to 100. Now you can see there's no distortion there. That's a nice looking sine wave. Now granted, it's out of phase, but that's not a big deal. And actually, you know what? It almost looks like there's some noise on that peak up there. But anyway, that's kind of moot, I guess. It's there, but I mean it's really small. I guess 500 kilohertz, it really kicks in. Now that's really messed up there. Wrong here. $700, $600. Anyway, distortion is an aspect of noise. So that's that circuit, and I want to look at I want to stop the sim. File, save. So if we type in we have to talk about noise. Distortion. Total harmonic distortion. So you can see different effects a circuit has. It's a high pass filter. I mean, you can avoid that by not going over the cutoff frequency, or under, as it may be. So anyway, that's just kind of showing you that distortion is, as an example of clipping, it goes over a threshold. That's not really distortion, that's just cutting off at a certain voltage. The creation of harmonics for the fundamental frequency of a sine wave into an input and intermodulation is something two different signals beating against each other and causing noise and such. But they don't talk about noise measurement in here very good, do they? Alright, so there's a good example on the right of noise and what it looks like on a scope, and what it looks like as an image, and you can do what's called spectrogram of noise. Let's do see if we can find a good sample here. Now here's another thing. Noise has color, and color is related to temperature. And they're not going to talk about that, I'll bet you, because it's advanced. Let's see. Maybe this chart. Okay, this chart here. Okay, see, now here you've got what's called this curve on the left. That's a typical normal distribution curve. Random thermal noise spectral distribution. According to this information, it's saying that thermal noise is a random noise that is based on a normal distribution. Now, in fact, there's a formula. Okay, spectral noise density is a noise power per unit bandwidth, expressed in watts per hertz, or dBm per hertz, represents the base noise power per unit, blah, 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 blah. Noise power computed for any bandwidth or temperature uses this formula. K times TE times B, W, blah, 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 blah. That's a bandwidth numbers. So if you have a narrower bandwidth, you're going to have, if you have a narrow bandwidth, you can have less noise. If you have a wide bandwidth, it's going to allow in more frequencies. So if you have a narrow bandwidth, that's your filter. You're filtering out a certain section. Like if you knew that your information was at 1 kilohertz, you would put a 1 kilohertz filter in there to filter that out and get rid of all the noise at that frequency. They're all, to measure noises, a reference noise source is used. The number There are a number of means to produce noise for reference sources. Among these are black body, thermal, plasma, electronic, and digital. They are all, except the digital, based on the noise power formula. Now, this is where I have a disagreement, okay? This formula is based on what's called Boltzmann's constant. And if you come down here, well, I guess black body noise, you see, they're using the same formula for noise, and yet thermal noise is based on a random distribution, where black body noise is not. This is not a random distribution, this color temperature chart. This distribution is based on what's called, I think, Planck's constants in this, but it says Boltzmann's constants in here. However, Planck's constant is related to Boltzmann's constant. And this is where I have a problem. And this chart, this formula has an addition. This classical theory is the ultraviolet breakdown, or whatever the heck it is. There's another formula that's added to that black body formula. If the wavelength exceeds a certain level, it switches over, you know. And there's temperatures in here that, you know, there might be something in here that approaches infinity, but yet it goes over infinity. It's like maybe a discrete number or something. I don't know. I'm going to look at that color chart in a minute. I just want to see signal to noise ratio. There's signal to noise ratio for your whole circuit. There's, you know, some things. You don't measure noise. It's better not to measure noise directly. You can, but it's not the general. Use a signal to noise ratio is what you do. This is a pretty good. So in other words, let's say you have a receiver. Where did that chart go? So you have a receiver, okay, and you put in, you load the receiver down with a load, and you, so that there's nothing coming in, and you take an average reading of the noise, or of the signal at the audio output. Then you increase a signal level into the receiver input, and as soon as the audio signal goes up by 3 dB, now you know what the sensitivity is of that receiver based on microvolts. That's that's your signal to noise ratio of the whole of the input. Noise source as an infinite bandwidth signal source. This is an RX noise bridge. This is comparing your unknown, which is your antenna, to this, and it's a very sensitive measurement, and talks about antenna gain, carrier to noise ratios. Audio measurement. I wonder what noise power ratio analyzer creates a noise source. Remote desktop. Well, let's take a look at the. Remember how I said Boltzmann's constant was related to. So anyway, it uses the most recent value for Boltzmann's constant, etc. Source temperature generally goes up linearly. Well, here it goes up non-linearly. This is the formula. B is the total bandwidth over which that noise is measured. And this is the power that would be absorbed from the component or source by a matched load. A matched load meaning you're measuring something and you're not interfering with what you're trying to measure. Still not happy with some of the stuff I'm seeing here. There's a noise figure. Why do they have this V squared and I squared over B? Spectral power density. Now let's look at Boltzmann's constant. Is a physical constant relating to the average relative kinetic energy of particles in a gas with the temperature of the gas, according to and occurs in Planck's law of body radiation. Okay. These are, what is this? R is a gas constant. This is the gas law. Thermodynamics, absolute temperature. talking about chemical kinetics. Role in semiconductor physics. Q is the magnitude of the electrical charge of electron. Equivalently, Vt equals Kt over Q. K, I'm assuming, is Boltzmann. At room temperature, Vt is approximately 25 millivolts. 300 degrees Kelvin it equals K over Q. Thermal voltage is also important in plasmas and electrolyte solutions in both cases. K over Q. Thermal voltage. Characteristic thermal voltage. In semiconductors, the Shockley diode equation, the relationship between the flow of electric current and the electrostatic potential across a p-n junction depends on a characteristic voltage called the thermal voltage, denoted Vt. This is the current and voltage characteristic of an idealized diode. Vd over Ti is diode current. Is is the reverse bias saturation. Vd is the voltage across the diode. Vt is the thermal voltage. Kt over Q. The equation is called the Shockley ideal diode equation when I did n is set to 1. Thermal voltage and arbitrary temperature. It is a known constant defined by this, where K is the Boltzmann's constant, T is the absolute temperature of a p-n junction, and Q is the magnitude of a charge, an electron, which is Q. That's an interesting equation. It's simple, but it's very interesting. Derivation. Cross-sectional area of the junction, and Fi is the number of incoming photons per unit area per unit time, with energy over the band gap energy is the outgoing photons. It integrates between infinity and Vg. This formula, FOV, is the outgoing photons. Although the analysis was done with photovoltaic cells, that's solar cells. Oh shit. Under illumination. It also applies when the illumination is simply background thermal radiation. It gives a more rigorous form of expression for ideal diodes in general, except that it assumes that the cell is thick enough that it can produce a flux of photons. When the illumination is just background thermal radiation, the characteristic is this. The reason why I am looking at this is because it's talking about Planck's constant, which is K down here. It's talking about photons going through that diode in a transistor. We can take that off, take that off. Boltzmann relation never expressed this until Max Planck first introduced K and gave it a price value of this. about 2.5% lower than today's figure, and is derivation of the law of black body radiation. Okay, so Max Planck devises the law of black body radiation, which is this, but it breaks down, and it breaks down in this looks like in this infrared area or something. It's called a. Now you see this curve is not a normal distribution. It's not a normal distribution. So extraterrestrial solar spectral irradiance, black body spectrum for T equals such. See, here they're calling it Maxwell-Boltzmann distribution. Is a particular probability distribution those are all your statistics formulas for CDF. What is CDF? We're talking about gases and plasmas. Distribution function. Thermodynamic temperature. Now, KT, you wonder why I talk about this? It's because there's a temperature formula in a diode. That's the voltages and current relationship. See, it's 0.3 volts for germanium, 0.7 volts for silicon. That's what that ideal diode was talking about there. Here's the equation for the diode. And so it talks about VT again. Oh, VT's up here. So VT, this temperature, or rather this thermal voltage, has Boltzmann's constant in here, and the temperature. That's the current through a diode. And we're going to be using LEDs. We're going to cut the top off of an LED to make it act as a receiver. This is the speed in milliseconds. Probability density speed. Probability density function. That's a normal distribution, PDF, of finding a particle with a speed near v. This equation is simply the Maxwell-Boltzmann distribution with a distribution parameter of a equals the square root of kt over m.
The Maxwell-Boltzmann distribution is equivalent to a chi distribution with 3 degrees of freedom. The simplest ordinary differential equation is satisfied by the distribution is this. The Darwin-Fowler method as a means of values of Maxwell distribution is obtained as an exact result. Cumulative distribution function. I'm not too much into statistics. I mean, I understand a little bit. Moment generating functions, properties. Moments have to do with energy points. This is a summation of e to the minus e over kt. It's a factorial, n factorial, quantum statistics. Bose-Einstein statistics. Summarizing both cases. Somebody knows what they're doing with math here. These are integrals, double integrals. This is summation. You summate, you add points from point A to point B. There's a shitload of crap. Method of steepest descent. So that's a little bit complicated. The most probable speed, Vp, is the speed most likely possessed by any molecule of the same mass in the system, corresponds to a maximum or mode of f sub v. To find it, we calculate the derivative of df over dv, set it to 0, and solve for v. See, again, they're talking about gas. That's kinetic energy of the speed of sound c in a gas. You better agree with me, bird. This stuff might mean something, it might not, I don't know. Okay, wave numbers has to do with every time an electron jumps in energy level, there's wave numbers associated with that. And it seems like there's a formula here, but I'm not worried about it. This frequency variable, Planck's law expressed in terms of different spectral variables. T is the temperature. I don't know what B is. Those have to do with energies again. Freeze out of high energy oscillators. Photon oscillator energies as HV over KT approaches infinity. So if you have a lower, oh, this is a negative though. If you have a lower temperature, you can make things go faster, maybe. Photons. Radiative heat transfer can be filtered. Black body. Remember its cosine law. Stefan-Boltzmann constant. The total power emitted per unit area at the surface of a black body can be found by integrating the black body's spectral flux found from Lambert's law over all frequencies. The difference in energy levels is your HV constant. What is HV? Is that Planck's constant times the velocity? V is the photon frequency. Maybe. There's a lot of crap in here. Log plots of radiance versus frequency for Planck's law. Okay, the Rayleigh-Jeans law, that's important. Now see, that also comes into some confirmation for whatever I'm trying to do here. It's approximation to the spectral radiance of electromagnetic radiation as a function of wavelength from the black body at a given temperature through classical arguments, where B lambda, depending on at such temperature, is the spectral radiance of power emitted per unit area. C is the speed of light, KB is Boltzmann's constant. T is temperature in kelvins. The Rayleigh-Jeans law agrees with experimental results at low frequencies, but strongly disagrees at short wavelengths. This inconsistency between observations and predictions of classical physics is commonly known as the ultraviolet catastrophe. Its resolution in 1900 with the derivation by Max Planck of Planck's law, which gives the correct radiation at all frequencies, was a foundational aspect of the development of quantum mechanics. Emitting more energy as the frequency increases. But begins to diverge with empirical observation as these frequencies reach the ultraviolet region. ultraviolet divergence. What is that? No, I can't get through all that shit. Let's read this. Results in the equipetition theorem of classical, which states that all harmonic oscillator modes of a system at equilibrium have an average energy of kT. That's the Boltzmann's constant. Illustrates millimode a natural vibrato string will oscillate at specific modes, the standing waves, and harmonic resonance, depending on the length of the string. In classical physics, the radiative energy will act as a natural vibrator, and each mode will have the same energy. Most of the energy in a natural vibrator will be in the smaller wavelengths at higher frequencies, where most of the modes are. It is clear that unphysical as the rotatory power of gravity is not observed to be infinite. That bird's gonna scream really loud in a minute. The correct form of the spectral distribution. Bose solved the problem by postulating that Planck's quanta were real physical particles, what we now call photons, not just a mathematical fiction. They modified statistical mechanics in the style of Boltzmann to an ensemble of photons. Einstein's photon had an energy proportional to its frequency. Shut up! Fucking bird. And is explained. He's gonna scream in a minute. Let me just open the cage up here. Also explain operation of the photoelectric effect. This spell is blah 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 blah. Shit. See, they're saying when we talk about photons, this is what we're going to be using in our experiments. We have to understand how we can. A photon has zero rest mass and always moves at the speed of light within a vacuum. The photon model accounts for anomalous observations, including the properties of blackbody radiation. That materials objects emit and absorb light in quantized amounts. That's discrete energy levels. Although these semi-classical models contributed to the development of quantum mechanics, many further experiments, beginning with the phenomenon of Compton scattering of single photons by electrons, validated Einstein's hypothesis that light itself is quantized. Protons and other elemental particles are described as a necessary consequence of physical laws having certain symmetry at every point in space-time. Lasers. So we're talking about lasers. Quanta is specific energy. Increases. Energy and momentum of a photon depend only on its frequency or its wavelength. The energy of a photon is given by hc over lambda. H bar is h over 2 pi is the reduced Planck's constant. So if we look at Planck's constant, is the quantum of electromagnetic action, which relates to the energy carried by a photon to its frequency. This is similar to E equals hf. Planck was able to calculate the value of h from experimental data on blackbody radiation. See, he was calculating the value of Planck's constant using blackbody, but what if in the other theory the Planck's constant breaks down in ultraviolet? The blackbody problem was revisited, etc., 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 independently proved that classical electromagnetism could never account for the observed spectrum. These proofs are commonly known as the ultraviolet catastrophe. In convincing physicists that Planck's postulate of quantized energy levels was more than a mere mathematical formalism. Here's discrete energy levels in this upper right-hand corner. When an electron jumps shells, a photon is emitted. That change in energy is equal to the speed and times Planck's constant. That energy level can be measured as Fourier transforms. The Schrödinger equation, which I believe is a wave, it relates your particles to your waves, okay? So all this energy that you see here, this wave function, this is a result of a bunch of photons being emitted over time. A double-slit experiment showing the accumulation of electrons on a screen as time passes. Those are crescent. That's a formula. Planck's quantization of light, and proposed the energy of a photon is proportional to its frequency, one of the first signs of wave-particle duality. Since energy and momentum are related in the same way as frequency and wave number in special relativity, it followed that the momentum p of a photon is inversely proportional to its wavelength. And wavelength is inversely proportional to frequency. So that means the momentum of a photon is proportional to the frequency. So the higher the frequency, the more energy that photon has. I'm not 100%. I'm talking about this because this is how we measure. This is how we're going to measure our energies. They're measured in waves. We measure waves. We don't measure particles. We measure waves. We measure particles over time. There's a bunch of complicated math in there. Don't need to get into it. Uncertainty principle is the idea that a particle can only be in such and such a place within a certain time or whatever. But these are all your basic energy equations. The Broglie wavelength has to do with the energy emitted during different energy level changes, etc. The Planck's constant is related to the quantization of light and matter. It can be seen in a subatomic scale constant In a unit system adapted to subatomic scales, the electron volt, which is what we measure, is the appropriate unit of energy, and a petahertz is the appropriate unit of frequency. Atomic unit systems are based in part on the Planck's constant. Green light is well interpreted by human eyes, a frequency of 540 terahertz. Each photon has an energy of so many joules. That is a very small amount of energy in terms of everyday experience. But everyday experience is not concerned with individual photons any more than individual atoms or molecules. The energy, its energy commuted by multiplying the photon energy. The Avogadro's constant with a result of 216 kilojoules per mole. About the food energy in 3 apples. That's cute. Rest of a mass electron. See, there's relationships between electron volts, photons, magnetism, being able to relate light and magnetism in such a way. Maybe it has to be done in the ultraviolet spectrum somewhere, because I've got a black light bulb. So Compton scattering, these are, see, there's your slit there. It talks about X-rays, but in reality it also has to do with energy of a photon at 500 keV and an electron after Compton scattering. That's 500,000 volts. Back to the photon here. Photon mass. Double slit experiment showed that light can act as a wave, helping to invalidate early particle theories of light. Well, that's not true. There are particles going through there, and the question is, how do they know where to go? 1900, Maxwell's theory of model of light as oscillating electric and magnetic fields seemed complete. However, several observations could not be explained by any wave model of electromagnetic radiation, leading to the idea that light energy was packaged into quanta, described by E equaled hv. In other words, if we create an energy, it's whatever this hv is, that's your photon energy. Later experiments showed that these light quanta also carry momentum, and thus can be considered particles. The photon concept was born, leading to a deeper understanding of electric and magnetic fields. These people still can't explain what a photon is. Listen to this wiki article. People just come in here and write these things, and they're supposed to know what they're talking about. There's no basis for information here. Where the hell are the numbers? Who the hell wrote this shit? This is bullshit here. Experiments confirm that the photon is not a short pulse of electromagnetic radiation. It does not spread out as it propagates, meaning it's not a particle, nor does it divide when it encounters a beam splitter. Rather, the photon seems to be a point-like particle since it is absorbed or emitted as a whole by arbitrarily small systems. However, photons can act like waves over time. Nevertheless, the photon is not a point-like particle whose trajectory is set probabilistically by the electromagnetic field, as conceived by Einstein. That hypothesis was refuted by the photon correlation experiment cited above. According to our present understanding, the electromagnetic field itself is produced by photons. Now that's interesting. Which in turn result from a local gauge symmetry and the laws of quantum field theory. So there's a statement right there that says electromagnetic field itself is produced by photons, meaning from a magnet. You're telling me that a magnet, there's photons jumping out of that magnet? The uncertainty principle for charged material particles requires that the quantization of light into photons and even the frequency dependence of the photon's energy and momentum. Forget what I just said. This delta x is equivalent to the wavelength over the sine of that angle. This shows the wave-particle duality of photons. Okay. Feynman diagrams. We're not getting into that. Photons in matter. Okay, let's do this then. Let's go. Now see. Maybe it has to be electromagnets. Let's look at this one here. This forms the basis of everything that I'm studying in interdimensional communications. Okay, look at this, see? This is important here. I'm gonna go grab me a little quick snack. There's more proof of what I'm able to do might actually work. But we gotta understand the basis of it so that we can know how to measure what we're trying to do. People think I'm crazy, I don't know what the hell I'm doing. They can all screw themselves for all I care. Hopefully my bird doesn't get too obnoxious. So, it says right here, the central idea of quantum theory is a duality between particle-like and wave-like structures behavior. Just as electrons and protons can interact as fields, the electromagnetic field can interact as particle-like quanta we call photons. In quantum electrodynamic theory, QED for short, charges and electromagnetic fields are described as interactions of quanta. This is most famously done through the diagrams, etc. That tells me that I can create an electrostatic charge of a high voltage, or an electrostatic field, and an electromagnetic field, and I can create photons from that field. It's saying that QED is allowing for interactions that are not forces. That didn't help very much. This guy, it says a magnetic field is not a static magnetic field from a magnet doesn't emit photons. Since photons carry energy. I don't think that's an appropriate statement. That's the momentum of a photon. Well, there is energy. That field would decay, contradicting the assumption it is static. An oscillating magnetic field can emit electromagnetic waves, which are bunches of photons. Bunches? This guy's got an MSc, a BSc, 28 patents, EM fields, communication theory, quantum mechanics, and relativity. Why do they put that stupid shit on there? It has references but no links. In a nutshell, virtual photons create the magnetic field observed from a permanent magnet. static fields. So for either electric or magnetic fields, that would be virtual photons that mediate the field. See Wikipedia. Now here this guy says, the magnetic field is the curl of the magnetic vector potential. The electric field is the negative gradient of the electric scalar potential. So there is scalar math involved here. How do we understand the vector and scalar potentials in terms of virtual photons? We should not think of photons as particles at all. A gauge invariant. Dirac's the photons are physical and the electrostatic force is instantaneous. When you have a solenoid, the photons are generated by the currents in the solenoid, and a charge moving through this virtual photon cloud has an altered energy, etc., 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 etc. That's a very confusing conversation. Talking about virtual photons. Let's look at images. So it looks like it's saying there's higher temperatures in the ultraviolet spectrum. Infrared is lower temperatures. That doesn't make any sense. It should be the other way around. Here's your light chart, okay? It's your visible spectrum. Ultraviolet is higher frequency. So that means in the ultraviolet spectrum, photons would have a higher energy. Alright, let me see that. So we got like a red laser, which is over here. Ultraviolet lasers. I wonder if there's a such thing as an ultraviolet laser. You see, light has spectrum. Okay, it's got all that energy. How to make an intense gamma ray beam. It's a good picture here. When an atom emits energy as photon as electron falls from higher energy orbital to lower energy. that this is how the spectrum works for different chemicals. A spectrum is a spectrum of light, and it's got little wave bands and stuff, and those are the these energy levels are when electrons move to different parts of the shell, or for whatever reason they give off a certain wavelength, and that wavelength is measured in terms of light and such. Electromagnetic energy. Brain waves as electromagnetic waves. What picture is this? Artist's impression. As an example, a chart of showing different spectra of different chemical elements like sodium, hydrogen, calcium. They give off energy levels. Now see, here's the thing here. It says electromagnetic radiation can interact with electromagnets while light cannot. However, if I put a magnet up to my oscilloscope, I can move the light beam. So the magnet is reacting with the electromagnetic voltage that's generating the light beam. The light beam is an indirect measurement of how much magnetic radiation has been changed. Which is almost making me think, why couldn't I just use an oscilloscope? The oscilloscope gives me a measurement. If I had that's why I was thinking maybe putting putting the energy into the RGB of a TV input, using those waveforms. That's something I want to mess with. Light can't. But light is electromagnetic radiation, though. It's just how it reacts. There's just always this thing about it, you know. Anyway, let's go back and look at, so diodes got voltage, there's noise. Noise in a diode, let's see. Yeah, we gotta talk about noise generators. using a Zener diode. Why a Zener? So if we build, when we build our, I'm not going to do it now, but when I come back, I don't know. When we build our amplifier, if we look at, let's take a look at this circuit again. Notice we've got an oscillator here. We might be able to use a noise generator in this. There's a noise generator in here. I've never used it before. So we know that in the circuit, if we go up to 1 megahertz, we get distortion, right? When we send a clean signal through there. Where's that up there? Why is that up there? How come it's not repeating? I have to wait for it to update. It's not updating or something. I don't know why this isn't updating. Don't ask me why it's doing something stupid now. Let's go up to 600 again. Why isn't it updating? Damn it, what's wrong with this circuit? I don't know what the hell is wrong. I don't know what's going on here. Maybe I had to move the scope. know why it's not updating now. It's being fucking retarded. I don't know what's wrong with this. It's not working. Alright, you know what? I'm just gonna fucking close the whole damn circuit here. Transistor amplifier, scope, turn that on, generator, turn that on, I wanted to run some noise through this. I don't know what's wrong. It's not working now. What the hell did I do wrong with this? Auto scale, mode coupling, cursor, I don't know why it's not going back like it used to. Are you seriously kidding me right now? Well, if I do the run stop thing, you can see there's no distortion. Okay, so let's do this. Let's go to noise. Let's put this down to 100 millivolts peak to peak. Okay, so you can see there's a noise being generated. Now if we look at the output, I don't know why that level is down there. Oh, I must have changed. I must have changed something. I must have changed this position or something. That's just a small change. Oh. Wait, what the hell? I don't know why that got changed. There's a lot more noise in the negative region. That's on the output, isn't it? So let's say if we had, if we wanted to look at, if we wanted to have let's see here, so we'll use a yellow line and we'll go, we want to have a low pass filter. So, but we want to have, we have to have this is usually an electrolytic. And we know what a low pass filter looks like. The high pass filter, wait, let me think. We want to pass everything below a certain cutoff. So a low pass filter is going to look like this. This is where, this is the circuit over here, and then so this is going to be resistor, and then we're going to have capacitor, and and we want FC to be equal to, we know that this particular circuit has distortion at 600 megahertz, and it's got severe distortion at, or 600 kilohertz, and it's got severe distortion at 1 megahertz or something. So let's do one for 100 kilohertz. And one for, let's say, 600 kilohertz maybe. And we'll use a resistor of, let's say, R equals 10K. We need to find out what C is. And of course we have capacitors to do that with, don't we? Let's see if we can use an online calculator here. Alright, so we've got 10,000 ohms. So we've got 10,000 ohms, and the C is going to be in farads. So it's 1 over. So we've got 1 over the frequency, 2 pi r, and C, whatever. So C, let's see, let's do a yellow here. C equals 1 divided by 2 pi r f sub C. Resistance is in ohms, capacitance is in farads, and frequency is in hertz. And we've got 1 divided over all of that stuff. So we'll do the first one first. So we'll do 100 kilohertz, 100,000 times 10,000 times 2 times 3.14. And we've got that number, and how do I just invert it? Do I do that? Well, I've got 6280 plus 6, 1 divided by 6280, 1, 2, 3, 1, 2, 3. So if we want to change that to nano, it's 159, 15.9 nanofarads, 16 nanofarad capacitor. I think we can do that. So let's see. So for 100 kilohertz, C equals 16 nanofarads. And now we've got to do it for 600 kilohertz. 1 divided by 2 divided by 3.14 divided by okay, that works. 1 divided by 2 divided by 3.14 divided by 10,000 divided by 600 equals 265. Wait. 1.6 centimeters. 10. 265 nanofarads. C equals 265 nanofarads. So if the capacitance goes up, the frequency goes down. Well, that doesn't make any sense, does it? Capacitance is supposed to be inversely proportional to frequency. Here the capacitance went up and the frequency went up. That doesn't make any sense. Oh my god, are you kidding me today? .16 nanofarads. If the frequency is higher, the capacitance is supposed to go down, not up. Three, 6. That's 1,000 with 6 zeros. And this is 6,000 with 6 zeros. What is it, 0.16? It's not 0.16 times 10 to the minus 9. God, I can't think straight. If I want to make that number bigger, I have to make the other number smaller. So it's 16 times 10 to the minus 9. One times 10 to the minus 9, 10. This becomes 10 times 10 to the minus 10. Oh, it's supposed to be 0.15? 0.16? No. I said it was 16. Because I'm going in the other direction. It's 16 times 10 to the minus 9. I don't know which way to go with this. This is 1.59 times 10 to the minus 10. I can't figure this out. I can't remember how to do this. I'm not having a good day. This is 37,680. This is 37,680. $265 times 10 to the minus 9. I don't freaking know, honestly. I don't understand it. I'm just effing baffled, really. Well, I could put these into the circuit and find out what happens. So I'll put a capacitor in. I'll put a resistor in. And another capacitor. This will be 10 microfarads. This will be 10K. And we'll do 16 nanofarads. So it looks like this is all in series, which in fact it is, but we take the output from the output of the capacitor. No. Where do we take the output here? The output across that capacitor. So now we're going to look at this point here. And we should see a cutoff below a certain frequency, shouldn't we? I have to go to the store. Look, it's getting light out. Wow. It's getting light out a lot longer now. I want to go back to frequency. and that's 100 millivolts, and change the frequency. We're at 100 kilohertz. The output's at 1 volt, the input's at 100 millivolts. So you can see if I go higher in frequency, there's no output because it's being shorted to ground. So let's go lower in frequency here. That's really getting shorted to ground pretty bad, ain't it? With that 16 nanofarad capacitor. I don't know what I did wrong. It might be the 10k ohm resistor. Something's getting saturated. Oh, it's the output. Oh, you know what it could be? It could be that coupling capacitor. I don't know, is it the coupling capacitor? Alright, well I changed it from a 10 microfarad to a 0.001. Yeah, I don't, it's that resistor probably. I don't know why that level's so low. Okay, see the level right there? It's pretty much like it's kind of going up when I've dropped the frequency down. Right now the level of the output is getting lower. There's no distortion in there though. No, now it's doing this stupid crap again. I think it froze. It's not distorted though. That's because that filter's in there. I wanted to see that distortion. That filter's taking out that distortion. Look at that. But and the level is so low. Let's put noise in there. What's wrong with this thing? The noise generator's not working. I don't know why the noise isn't working now. Alright, screw this. I can't fuck with this anymore. What we're gonna do is we're gonna get rid of this generator. And I'm gonna put in, well, first we're gonna put in a resistor. And I'll tie that to ground. And I'm going to make this value, well, let's leave it as a 1K for now. And the reason for doing that was what we're doing is we're shorting the input via a low impedance, which is relatively a low noise source. It's just in the thermal noise across that resistor. Now, being that it's ideal, can see there's just it's like there's not much there. There's a little spike there. There is some noise there. I mean, I generally want to be in the microvolt range. Right. I'll turn this off. Now I'm going to change this to, let's change it to 100 megohm. Now it's a NPN BJT transistor, bipolar junction transistor. So it may not have as much of a noise on the input. And as you can see, it pretty much doesn't. It's generating some spikes. So that could be, well, whatever that is, it's just generating some noise spikes in there. Now, when we go back to, there's a Zener diode. Let's put that in there and see what happens. Wait a minute, what did that look like? Probably just a DC voltage. Diodes, Zener, 5-volt Zener diode, and we will use let's change this to 100K. Actually, let me look at that circuit. Yeah, I don't know. It talks about bandwidth and that sort of thing, but this would generally be a lot lower resistor. Let's make it a 1K. There's still no noise there. If I make it a high voltage, it's not going to... I don't think it's going to do anything. Where we get the good effect for amplifying noise is with that FET. I may have to build up that circuit. Yeah, it's not working very well. What if we just throw an FET in there? That's a gas FET. JFET. I think I connected it already. I can't get that mess out of there. Why is that line connected to ground? Let's start this up. I think I'll have to build up these circuits manually by hand because the simulator is not doing some things that I want it to do. Yeah, it's still showing. Yeah. Shit. Well, that's... Damn it, you know what I want to do? Oh, shit. You know what it did? It automatically saved us. I can fix it. Alright, what I'm going to do is I'm going to take this filter. So what we're going to do is we're going to measure channel 1 is our input. Wait, That's our sync line. And the signal to here. We're going to go measure back on the output again. I didn't get that noise to work the second time. I don't know why. I go get me some strawberries. I thought I got a message earlier. Maybe I should take a lookie. Someone try to call me. No. Put a signal in, frequency, it's frozen a little. So the red is the input line. No distortion. How did I get that color to change? I didn't do anything. Now it's not distorting. It's not distorting now. Oh, it could be because of the input level. When you increase the input level, I mean, that's 100 millivolts on the input. Well, I don't want to get into clipping. It's not even working now. It's not showing that distortion. Oh wait, there it is. Okay, there's the distortion. That's what I was looking for. But when I do a noise, if I input noise, that's 600 millivolts peak to peak. That's 500 millivolts peak to peak. There's some distortion there. Let's hit noise. Now see, noise is a combination of everything, so there's going to be distortion in there. And so what I'm wanting to do is I'm wanting to get rid of that distortion, but I don't want to lose my amplification. You know what I mean? I'll have to work with those components when I actually build a circuit or something. I think it must take it a lot longer to build that noise generator in the circuit or something, you know? It's just not working for me. It says sine wave. So I'm going to shut this off. Maybe we can build this circuit. It's not such a bad circuit, and it's got the distortion. And we found that if we added a filter on the output, even though we cut it off, that filter is going to take out harmonics. I wonder if that's because of the input capacitor. That's a 1 microfarad. That's a high pass filter. I changed that input capacitor from a 1 microfarad to a 0.001, which is a 1 nanofarad. But I've left the frequency the same, so we're going to see if we see that distortion in there. It started out with a little distortion. Oh, there's distortion there. Yeah, there's still distortion in there. It looks good at 500. So I could probably put a 10 nanofarad in there. So it will take out, if I put the filter in, it takes out the distortion. So which I guess that's a good thing, because distortion adds to noise. If we get rid of distortion, that's one aspect of noise that I won't have to worry about. Let's do it. We'll do it when I come back. We'll make the circuit. Now, the other thing is there's noise circuitry, there's some things in there, but there's noise temperature that I was talking about. We were talking about the transistor, the history of the transistor, how it came, a little bit about how it came about. It's a vacuum tube. Oh yeah, they didn't have that. They had vacuum tubes first, didn't they? That was the predecessor before the solid state transistor. Well, anyway, let's do something here. I got tons of vacuum tubes too. They act as there's rectifier tubes. There's a heater element, which is usually at 16 volts AC or something. Heats this. You have the anode. It's basically like a diode. Anode, a grid, a heater, a triode, diode. Electrons from the hot cathode flow towards the positive anode. So there's a diode tube. That's where these electrons are floating around in free space here. We could drive a laser beam through there and interact with them photons or electrons or whatever's up in there. Fleming's first diodes. That looks like a spaceman. The heated filament was capable of thermionic emission of electrons that would flow to the plate when it was a positive voltage with respect to the heated cathode. However, electrons could not pass in the reverse direction because the plate was not heated. The Fleming valve could be used as a rectifier of alternating current and as a radio wave detector. This greatly improved the crystal set which rectified radio signals using the size based on the so-called cat twister. The grid is like the base on the electron. The transistor. Your plate's on the top. The cathode's on the bottom, and the heater's down here. It's the amplifier tube. But there's electrons going back and forth there. You get into op amps, comparators, transistor circuits, distortion. We're talking about noise. Color of noise. Noise has a temperature. Talk about all that good stuff. There's this chart I want to get back to. Here's your temperature of noise. So, I don't know what that infinity symbol goes down into the ultraviolet region. Your hotter temperature, well, it looks like your hotter temperatures are down there. So that's that. Noise and noise measurements. Lamp noise source. Electronic noise sources. Minimum detectable signal is determined by the receiver noise figure. That number is minus 174 dBm per hertz plus the noise figure dB plus the bandwidth that you're trying to measure. When the temperature of the system under test is not at 290 degrees Kelvin, which is room temperature. For a receiver with the estimate performance level, and just adds the signal to noise factor. There's the formula VRMS. Arms noise current VRMS units is the square root of 4 times the Boltzmann's constant times the temperature times the bandwidth times R, which is something. When you mix signals together, there's an inherent noise, which is called intermodulation distortion. And that I wouldn't think that would happen if you're just adding noise to a signal. So I'm not going to worry about it. Zener diode noise is less than 50 microvolts. 300 Hz to 15 megahertz. Noise voltage of an avalanche diode. Filter circuits. Some LEDs of various colors from various manufacturers displayed no measurable noise when measured. Zener diodes are a low ohmic source of noise voltages, internal resistance less than 50 ohms, with a spectrum which extends up into the megahertz range. Temperature coefficients in millivolts per degree centigrade. There's some diodes, LEDs. A 5.6 volt Zener has no temperature coefficient. The higher voltage Zeners have a higher temperature coefficient. The LEDs have negative temperature coefficients. The 1N4148 has a negative temperature coefficient. Alright, I'm putting this is the amplifier I want to build for the FET. I thought there were some numbers here. There's one there. Let's get a 2 megohm input impedance. That's a MOSFET. FET amplifier. There's a 2N3819. Control voltage. There's a circuit to build. Source follower. Offset biasing is applied via 1R and R2. 2 megohms. Constant current generator Q2 acts as a very high input impedance source load, giving the circuit an overall voltage gain of 0.99 C2 up to 1000, which is shunted by the J50K. The input impedance of the circuit is 500 megohms. Note, even if the high factor of this circuit is to be maintained, output must be taken to external loads via amplifier to fairly high impedance loads. Hmm, 15 hertz to 250 kilohertz. This high shunt value is high shunt value. A self-biasing preamp. Bandwidth over 100 kilohertz. I gotta go to the store. Yeah, DC to AC. So those are pretty good circuits. This is this might work. I like this general purpose preamp. I don't like the idea of, I like figure 12. This figure 12. Wait, figure 12, figure 13. And this one, the hybrid, this one, 8. I don't know what the 31904 does. Those are MOSFETs. power FETs. JFET amp versus a triode. Ooh. That's interesting. Tube circuit has more headroom and a bigger presence in the bottom end, but the JFET amp is very clean in the upper end. It has a very flat and tight low end. Clean in the upper end meaning the higher frequencies, which that's what we're looking for. The fun starts when you overdrive the shit out of it. The distortion characteristics of a JFET based mic preamp jumping pad one to unleash a palette of sonic evil. JFP gain module. Well, this is interesting. This is really interesting that I discovered this. I'm going to stop there. Where's my... We'll be back in a bit and